Okay, thank you very much. So in this talk, we consider a variant of the traveling salesman problem. So it's the ST path traveling salesman problem. So we're given a vertex set V and a distance metric on the vertices. And we have two special vertices, S and T, and our goal is to find a path that starts from S, ends at T, and visits every other vertex on the way of minimum total length. So it's well known that equivalent to this problem, it's finding what we call a minimum cost ST tour. So we want a graph G that is connected and in which every vertex has even degree except for S and T, which should have odd degree, right? So then such a graph, you can just traverse it, shortcut the traversal, and get a ST path TSP solution. So that's what we're going to do. We're going to find a connected multigraph G in which every vertex has even degree except for S and T that should have odd degree. So this problem was first considered in a paper by Hoogeveen, who showed that the Christophidis algorithm for this problem gives you a 5/3 approximation. And in recent years, when there was lots of interest in different variants of the traveling salesman problem, this problem has been considered as well. So Ann, Kleinberg, and Schmoys improved the guarantee to the golden ratio by taking a variant of the Christophidis algorithm that I'll talk about in a second. The analysis of this algorithm was improved by my co-author, Andras, to 1.6, then it was improved a little bit more by Wiegen, and then last year, Gottschalk and Wiegen slightly changed the algorithm again, and I will talk about what they did to improve the ratio to 1.566. And so our contribution is we improve the approximation guarantee and also the upper bound on the integrality gap to less than 1.53. So we have the gap between the previous result and the conjectured bound on the integrality gap, which is 1.5. In terms of techniques, one thing to highlight is that we are using deletion. So we start with a connected graph and delete some of its edges. That was, of course, used by the famous paper by Mumke and Svensson for graph TSP for the cycle case. But this is the first work, as far as I know, that uses this for general metrics. Okay, so if you've never thought about this problem, then it's not obvious that actually Christophidis' algorithm doesn't just give you a 3/2 approximation for the ST path TSP. So why does it not? So Christophidis' algorithm, right, you start by finding a graph that's connected, so a minimum spanning tree. The cost of a minimum spanning tree is, of course, upper bounded by the cost of the optimum, since the optimum is connected. And then you're just going to fix the parities of all the nodes. So S and T, or we'll define a set S, T sub S, which contains S and T if they have even degree in the spanning tree, and any other vertex is contained in TS if it has odd degree in the spanning tree. And so we find a TS joint that's a set of edges such that the nodes in TS have odd degree, every other vertex has even degree. So if we add that to the spanning tree, we get the correct parities. So in the case of the traveling salesman cycle problem, the cost of the TS joint is upper bounded by half of the optimum, but this is not the case in the ST path TSP case. And so we cannot just get a 1.5 approximation that way. So to think about the cost of correcting the degree parities a little bit more, that we can use the TS joint polyhedron. So we'll have a decision variable y for every edge. Y is indicating whether the edge is used to correct parity. So in the TS join, we're trying to minimize the cost of the selected edges. And then we have the following constraints. So here's an example of a tree. The red nodes in the tree are the ones that have the wrong parity, right? S and T should have odd degree, so they're good. 2 and 5 should have even degree, so they're good, but the other nodes have the wrong parity. So now if I look at a subset of nodes here, if it has an odd number of nodes in TS, then my TS joint should have at least one edge going out of that set. And here's another example. So another way of saying that you need at least one edge out of a set of vertices that had an odd number of vertices in TS, you can say, well, if you think about a set of edges, Q, which is a cut in the graph, if the tree S does not have the parity in that cut that an ST path solution should have, then our TS joint should cross that cut. So here's an ST cut, which has 2 edges in the cut, but of course, a path should start at S and end at T, should have an odd number of edges in such a cut. So there's a constraint that says that the TS joint should have at least 1 edge across that cut. Here's a non-ST cut, which has 3 edges, but of course, an ST path solution should have an even number of edges there. So the TS joint should have at least 1 edge across that cut. Okay, so here's the TS joint polyhedron again. The sum of the values across a cut Q should be at least 1 if the tree is odd across Q and Q is a non-ST cut, or if the tree is even across Q and Q is an ST cut. So it's well known that the TS joint polyhedron has integer extreme points. So in order to upper bound the cost of correcting degree parities, it suffices to just find a feasible vector for this polyhedron. And in the case of the cycle TSP, we can just do this by taking half of the LP optimum for the TSP problem. So we could think about the same thing here. Can we use the vector y, which is x star over 2, where x star is an optimal solution to the LP relaxation? So if a cut Q is not an ST cut, then the LP relaxation has to have at least 2 edges in that cut. So there that works. But of course, if the cut Q is an ST cut, then our constraints of the LP are only going to say that you need to cross that cut at least once. And so for these cuts, if the tree has an even number of edges across the cut, we're not guaranteed that x star over 2 is at least 1. Okay, so we don't have a 3 halves immediately, because if we take the LP relaxation solution and divide it by 2, that will violate the TS joint constraints only for ST cuts, such that the parity of the tree in that cut is wrong, so it's even, and the cut is what we call narrow, so the x star value across that cut is strictly less than 2. If it's at least 2, we're still good. So I'll call the deficit for parity correction for a narrow cut exactly how much we're short. So 2 minus the total value that the LP has across the cut divided by 2. So that's parts of an edge. And we have that deficit only if the tree is even across the cut. So for example, if the cut has a total value in the LP of 3 halves, the deficit is 1/4 if we have a tree that is even across that cut. Okay, so of course, what we just need to do is find a low-cost way to make up the deficit. So we'd like to actually make it up for free so that we get a 1.5 approximation, but as low cost as we can. And a helpful fact here is the observation by Kleinberg and Schmois that the narrow cuts form what they call a chain. So here's an illustration of that. We've got a small example here with an LP optimal solution indicated. This is an example from a paper by Gao. So we've got edges with x value 1, 2/3, and 1/3. And so the narrow cuts form this nested chain. They're indicated by the gray edges. And so we've got cut here which has a total value of 1, and another cut here with a total value of 1, and these other cuts have a total value of 5/3. Okay, so how do we deal with these even narrow cuts, right? So they're only a problem if the tree has an even number of edges across the narrow cut. And so Kleinberg and Schmois proposed this variant of the Christophidis algorithm called best of many Christophidis. So you decompose the LP solution into a collection of spanning trees. Then not all of those trees are going to be even across a narrow cut. And so it's not always a problem that you have a deficit. So they show that then you can sort of correct parity using x star over 2 plus a little bit more. So they don't quite show that this is 1/2 times the optimum, but of course the connectivity still, the cost of that can be bounded by the optimum. So first part works the way we'd like it, second part not quite. Another approach by Gao in 2013 is for the graph TESP case, or graph SD path. So we're given an unweighted graph. Our metric is just the metric completion of that graph. So he showed that you can always find a minimum cost tree that has exactly 1 edge across every narrow cut in the graph TSP case. So in that case, right, we take that tree that has 1 edge across every narrow cut, so then there are no even narrow cuts. So the cost of correcting parity is at most half of the LP optimum, so that part is good. But in the weighted case, this first step will be more expensive than the optimum. Okay, so one last thing from the recent literature that is going to be helpful for us as well is what Gottschalk and Wiegand showed last year. They showed basically a generalization of the idea of Gauss here. They showed that X star can be decomposed into what I'll call locally Gauss trees. So it's a collection of trees with an order associated with it, such that for each narrow cut Q, the first 2 minus X star of Q fraction of the trees have one edge in that tree, right? So a Gauss tree is each narrow cut has one edge in, so each narrow cut has one edge in the tree, and now it says the first 2 minus X star of Q have one edge in the cut Q. So for the example I showed before, 2 minus X star of Q is 1 for these two cuts and 1/3 for these. So I want to decompose this LP relaxation into spanning trees, or write it as a convex combination of spanning trees, such that the first 1/3 fraction of the trees have one edge in these 4 cuts, and all trees have one edge in Q1 and Q6. So here's such a decomposition. I've got 3 trees. Each of them have a weight of 1/3, and you can check that if you take 1/3 times this, plus 1/3 times this, plus 1/3 times this, that exactly gives you this LP solution. And in this first tree, all of the narrow cuts have exactly one edge in the tree, and in the later trees, the S cut and the T cut have one edge, and the other cuts I don't care about. They can be anything. All right, so now what do? We start with this decomposition of Gottschalk and Wiegand. And so now we're going to look at those cuts where those cuts and those trees where we're guaranteed that there's only one edge in the cut. In those trees, we'll call the edge in the tree in the cut lonely. And the weird thing is, right, in those trees and those cuts, we're actually good because we have an odd number of edges across that cut, and that's what we want. But we're going to actually delete it so that we don't have an odd number of edges anymore. Then we're going to correct the parity with a carefully chosen T-join, and then we'll have a solution where every degree parity is correct, but it's not necessarily connected because we deleted edges at the beginning. So we'll correct connectivity by adding back doubled lonely edges we deleted before. And then we output the solution of minimum cost. So here's how that would work on this first tree of the decomposition. So in this tree, almost all of the edges are lonely edges. They're guaranteed to be the only edge in a narrow cut. I delete all of those edges. So once I've done that, I have a forest left containing only one edge. And almost every node has the wrong, which nodes have the wrong degree parity now? So S and T should be odd, so they have the wrong parity. 1, 2, 5, and 6 should be even, and 0 is even, so they have the right parity. And 3 and 4 have the wrong parity. So I add edges to correct the parity of all the nodes this way. So now I have a solution where every node has the right parity, but of course it's far from connected, so I add back edges I deleted previously, but doubled, so to get an ST tour. Okay, so this looks really horrible in this picture, right? This is much, much worse than we could have done. Our algorithm is not going to choose these red edges as a T-join. It will typically choose something that automatically already connects back things that we disconnected by deleting edges. So in particular, we show a distribution over red and blue edge sets such that the expected number of red plus blue edges across any lonely cut Q is at most how much the LP had across that cut. And remember, right, a lonely cut is a narrow cut, so it has fewer than 2 in the LP, so we use fewer than 2 edges across the lonely cuts in expectation. Now, what were we aiming for again? We would like to get a 1.5 approximation, so that would be 1 edge for connectivity across the cut, and the LP value over 2 edges for parity. So we're actually doing better than what we were trying to achieve. So we can show that for a given narrow cut Q, if the tree has one edge in that cut, then deletion actually allows us to do better than what we would like. So we would like to get the tree plus x star over 2, and we're saving this many parts of an edge for that cut. Of course, we also know that if the tree has an even number of edges in Q, then x star over 2 had exactly a deficit that's equal to that amount for parity correction. So as long as the weighted fraction of trees in which Q has a lonely edge, so where we're saving, is at least as much as the weighted fraction of trees in which we have a deficit, then the saved edge part can pay for the deficits. And we can guarantee that if the value of the LP across the cut is 3/2, then you're saving at least half of the time. So that tells us that if we take an LP optimal solution and no cut has value between 3/2 and 2, so either it's less than 3/2 or it's not narrow, then there exists an ST tour of cost at most 3/2 times the LP optimum. Okay, so that works in this special case. How about in a general case? Well, then a cut Q may save less often than it has a deficit. So how do we deal with that? Well, we're going to deal with that by basically changing our baseline that we're comparing to. So right, we have a deficit for ST cuts only. So if we add something to x star over 2 for every ST cut, then our deficit goes down and actually also our savings go up. So we're going to add gamma times the incidence vector of the ST path in the tree. So that means that our deficit goes down by gamma, our savings go up by gamma, but of course the thing we're comparing to goes up by gamma times the ST path. And you can show that if you choose gamma to be 1/16, then for any value of x star Q, the total amount you save is at least as much as the total amount you have in deficit over all trees. So if we can summarize that by saying that we can always find an ST tour of cost at most 1.5 times the LP plus 1/16 times how much we added. And that was, right, if we let P star be the average of the incidence vectors of the ST paths in our trees, that's how much we added to make the argument on the previous slide work. Okay, so that doesn't give us any approximation algorithm yet, but it does once we combine it with this observation. So this was an observation in Hoogeveen and also used by Andras. If you take x star to be an optimal LP solution, P star is the average of the incidence vectors of the ST paths in the trees. There always exists a tour of cost at most 2 times the LP minus the ST paths. And that's just by thinking if you take any tree, double the edges that are not on the ST path of the tree, that will give you a solution that's connected and in which all nodes have the right parity. Okay, and now we can just take the minimum of these two tours, and that has cost at most 3/2 plus 1/34 times the LP optimum. Okay, so to summarize, right, we get an approximation guarantee and integrality gap bound of 3/2 plus 1/34. We give a simpler framework for analyzing these best of many Christophidis algorithm, and right, we use deletion in arbitrary metrics to get an improved result. So it mixes the parity and connectivity stages of the algorithm. One last thing is that we also show in the paper that you don't actually need to compute the Gottschalk-Wiegen decomposition. You can use a set of trees computed by a greedy algorithm and still get the same result. Okay, and then of course the open question that's obvious here is let's get rid of that last 1/34 from the approximation ratio. Thank you very much. So the trees, you can find them in n log n time, but you need to know what the narrow cuts are. So you need to solve the LP to know that.